You're driving home from work. Ahead of you is a highway that usually takes exactly 20 minutes. You know every pothole and every curve. But today, right as you approach the on-ramp, your phone pings. Google Maps tells you to ignore the highway entirely and take a bizarre, winding detour through a quiet residential neighborhood. It feels counterintuitive. You can see the highway right there, and it looks completely fine. But you trust the app, take the turn, and 15 minutes later, you pull into your driveway. Later, you check the local news and see that the highway you almost took became essentially a parking lot due to a massive multi-car pileup just beyond the horizon. How did your phone know? It's tempting to think there are thousands of cameras watching every single intersection, or that a fleet of satellites is tracking every individual car from space. But the reality is much more elegant. It doesn't rely on cameras. It relies on a massive, invisible, mathematical network that you are already an active part of. To understand how Google Maps beats traffic in real time, and how it practically predicts the future, we have to deconstruct the three layers of its digital brain: the graph, the swarm, and the oracle. First, we need to understand how a machine actually sees a city. When you look out your window, you see asphalt, buildings, traffic lights, and trees. Maps doesn't see any of that. It strips away all the physical matter and reduces the entire world into a pure mathematical structure called a graph. In the world of computer science and graph theory, every single intersection or dead end is called a node, and every road connecting them is called an edge. To get you from point A to point B, the application doesn't just look for a road. It runs a highly optimized routing algorithm, often utilizing variations of Dijkstra's algorithm or A-star search. These algorithms calculate what engineers call the cost of traveling across each edge. In a perfect, frictionless world, that cost is simply the physical distance of the road divided by the legal speed limit. If you want the fastest route, the algorithm rapidly searches through thousands of branching paths, adds up the mathematical costs, and simply picks the lowest number. But as we all know, the real world is incredibly messy. Speed limits are entirely irrelevant if a road is clogged with bumper-to-bumper traffic. Furthermore, calculating the perfect route across a massive graph like the entire United States would take far too long for a mobile phone to process. So, Google uses hierarchical routing. It prioritizes massive highways as primary arteries and only looks at local roads when you get close to your destination. Yet, to calculate the real, dynamic cost of any road at any given second, the algorithm needs data, a staggering amount of it. And that brings us to the second layer of the system. In the early days of GPS navigation systems, live traffic data was almost primitive. It came from physical, expensive sensors installed directly into the asphalt of major highways by local governments, or from traffic cameras. It was slow to update, incredibly costly to maintain, and it completely ignored 90% of local streets. Google's solution to this bottleneck was entirely brilliant. Why spend billions building new sensors when almost every human being on Earth already carries a highly advanced sensor in their pocket? If you use Google Maps with location services enabled, your phone is constantly sending tiny, anonymous bits of data back to Google's servers. It isn't just sending your GPS coordinates, it sends your velocity, your trajectory, and even data from your phone's internal accelerometers. When you aggregate this data from millions of active users in a single city, the system creates a live pulse of the traffic. It can instantly see that the average speed on a specific stretch of interstate has plummeted from 60 miles per hour to barely 15. The central algorithm instantly updates the cost of that specific edge on the graph. The line turns red on your screen, and the routing algorithm instantly starts branching out, desperately looking for a cheaper mathematical detour. But raw data is notoriously dirty. What if a postal worker is stopping at every single mailbox on a street? What if someone pulls over to the shoulder to take a phone call? What if you are riding a bicycle on the sidewalk next to the road? If maps took every slow-moving phone literally, it would constantly create phantom traffic jams all over the city map. To fix this, Google utilizes complex anomaly detection algorithms. By analyzing acceleration patterns and the suddenness of stops, the system filters out devices that aren't behaving like normal vehicular traffic. Although it isn't entirely flawless. In 2020, an artist named Simon Weckert famously hacked Google Maps without writing a single line of code. He simply dragged 99 second-hand smartphones in a small red wagon down a completely empty street in Berlin. The app saw a dense, slow-moving cluster of devices on the road, assumed it was a massive traffic jam, and painted the street deep red. It actively rerouted real cars away from a completely empty avenue. Google engineers actually appreciated the stunt, and they have since updated their anomaly detection algorithms to recognize when a tight cluster of phones is moving together in a small cart, rather than acting as separate vehicles. They learned to distinguish between the micro-movements of a person walking and the suspension of a car. So, crowdsourcing is fantastic for knowing exactly what traffic looks like right now. But here is the fundamental problem with navigation. If your daily commute takes 45 minutes, it doesn't matter what the traffic looks like right now. It only matters what the traffic is going to look like 45 minutes from now, when you actually reach that final stretch of your drive. To accurately predict the future, Google had to look beyond basic algorithms. They partnered with DeepMind, their highly advanced artificial intelligence research lab. DeepMind implemented a sophisticated machine learning architecture, specifically known as a graph neural network, or GNN. Traditional machine learning models are excellent at analyzing isolated sets of data, but a GNN is designed specifically to understand networks. It inherently understands spatial and temporal dependencies. It knows that what happens on one street will inevitably spill over into the surrounding streets, creating a butterfly effect of congestion. Think about a stalled delivery truck blocking a major bridge. The GNN doesn't just see a red line on the bridge. It calculates the cascading effects. It knows that within 10 minutes, the off-ramps will back up. Within 20 minutes, the local intersections attempting to bypass the bridge will gridlock. It predicts how human drivers will aggressively try to outsmart the traffic and anticipates the chaos they will create. The neural network constantly analyzes decades of historical traffic patterns, knowing, for example, that a specific tunnel always slows down precisely at 5:15 p.m. on Thursdays, or that a light drizzle of rain will slow down a specific highway by exactly 12%. Then, it fuses that historical knowledge with the live, crowdsourced data from the swarm. If the GNN sees a sudden, unexpected slowdown on a highway, it instantly calculates the ripple effect across the entire city grid. Because of this highly trained graph neural network, when Google Maps gives you an estimated time of arrival, it isn't based on the traffic that exists right now. It is based on the traffic that the artificial intelligence predicts will exist at the exact moment your car arrives at each specific segment of your journey. Every time you open the app and type in a destination, you are actively participating in one of the largest continuous computational experiments in human history. Your phone sends a ping. A graph neural network processes it alongside millions of others. A routing algorithm recalculates the mathematical cost of a massive civic infrastructure, and a clean, simple line on your screen tells you to take a left turn. It isn't magic. It's just the elegant application of graph theory, an ocean of crowdsourced human behavior, and a predictive artificial intelligence, all working perfectly together in the background, just to save you 5 minutes on your drive home. If you want to understand more about the invisible systems, algorithms, and engineering that quietly run our modern world, make sure to hit the subscribe button. Let me know down in the comments which everyday piece of technology we should deconstruct next. Thanks for watching. If this video helped you understand the world just a little bit better, drop a like and make sure to subscribe so you don't miss our future deep dives. The YouTube algorithm loves it, and it really helps the channel grow. Also, I want to hear from you. What everyday system, app, or hidden technology should we deconstruct next? Let me know down in the comments below. Thanks for watching, and I'll see you in the next one.